All right, here we are for another exciting Chapter 9 lesson, and we will be wrapping up Chapter 9. We've covered most of this stuff, but I want to make sure that we are super clear on how to work a lot of these problems, because while most of y'all got most of the things right on the quiz, and the class average kind of showed that. Pretty good job on that, but clearly we got a little bit of misconception on some of the stuff, and maybe not misconception, but just we could use more practice working problems. And so I think probably what's the best thing for us to do is just to work a problem from each one of these sections that will be like something on the tests that we've got coming up. That way you guys will feel like you've got maybe a little bit better of an understanding of what's going on in those problems as we move into the little bit more complex ones of like the ideal gas law. Because we had a good bit of trouble, and some of that was, and on at least one of it was my poor problem writing. And I also want to make sure we focus on, this is one thing I also need to add, is the absolute versus gauge pressure. And the differences of those, and just how we make sure that we are keeping our thoughts very clear on that, because this can actually get pretty confusing pretty quickly. That I probably didn't take it, I didn't think it through really enough on making sure I was clear about that. I sort of was treating it like a simple addition problem like I did on your quiz. Hey, here's your gauge pressure. What's the absolute pressure? Like you just add in atmospheric pressure. But if you're not sure which one to use, it actually can be pretty confusing, because you end up with like, hey, we didn't have any pressure on it and it was 0, like in your lab. And so I'll try to clarify some of that to make sure we are clear on what needs to do what when. All right, so we're just kind of hanging out in 9.2 and 9.3 here. And we're just going to pick a couple of problems, just work through and talk through those. And that'll probably take us most of the class. And then I will have, if it doesn't, I'm not quite sure how long it's going to go. But if we have some time left over, I'll send some work for you guys to work through together as a class. And I think that's going to be the most effective use of this class period. All right. So, and also, you have to pardon me if I start sniffing and sneezing. The allergies are acting up, and there's not much to be done about it, to be honest, on a day-to-day basis. So just bear with me there, guys. All right, so let's just jump right in here. All right, let's just start out with something pretty straightforward, and let's look at number 16. Okay, so if you guys will flip back there, that'd be great, and let's see what we've got going on. All right, so anytime we've got a problem, if you are at all confused about what to do, how to get started, a good way to organize your thoughts and get your problem solving head on straight, you just need to start labeling your variables, okay? And so on 16 it says weather balloon is filled with 275 liters helium at 29 C and 765 millimeters Hg. Volume then is 275 liters, and let's just say that the gas is helium, just in case we need that later. All right, we've also got temperature is equal to 26 degrees C, which is equal to Excuse me. All right, we need to go ahead and change that into Kelvin for our temperature. All right, and then we've got what? We've got pressure is equal to 765 millimeters Hg. And just remember that that's also equal to torr, just in case that makes it a little bit easier to do some of your conversions or find out which gas constant you need to use. All right, so we need to know number of moles of helium are in the balloon. So that's N equals question mark. Okay, so this should be pretty straightforward. So PV equals nRT. And let's just sub in and see what we've got and see where we need to go. Okay, so we could flip back, put a marker there, and then flip back to your R. All right, and so what are our R values we need to get? We got millimeters Hg, we've got liters, and so we can use all right, sorry I had to pause you there for a sneezing attack. All right, so our R is 62.36, and that of course is just from page 235. All right, so now let's fill it in. What have we got? We got 765, and our volume is 275 liters, millimeters Hg. N is what we're looking for. R 62.36, and T, of course, is 299.15, and that's K. Always got to be K, guys. A lot of mistakes about that on the quiz. I think that was the #1 thing that I was taking points off for at various different times for various different people. And some of y'all figured it out like halfway through the problem that you needed to be in K and then didn't necessarily go back and fix it. So just slow down, be careful, and yeah, that'll do a lot for you. All right. So and again, because and I know some of y'all are just rolling your eyes that I'm doing this, but again, we've had just some stuff that I see on these quizzes, and I don't know if it's carelessness or what's the deal, but basic algebra problems. I know your algebra teacher pretty well, and she'd be really disappointed with how some of you guys are going about solving these problems. It's really not a good thing, we'll say, if you get to here and then you're not quite sure where to go. Okay, if you aren't sure how to solve from here, and you're consistently getting the wrong answers, first of all, if this is happening in your homework, that you're getting here and you're finding out that whoops, that's wrong and that doesn't match the answer. Oh wait, but if I do it this way, that does get the right answer. You need to stop. And you need to look at how you're solving your problems. And you need to figure out what it is that you don't understand about this situation here. And come talk to me about it, talk to Mrs. Forster about it, talk to somebody about it, what's going on. We would love to help you understand what to do, but don't just keep giving up the points, and then look at it and sort of, maybe slap your forehead and be like, how did I miss that again? Notice it in your homework, okay? We're doing plenty of homework, plenty of math. You should be always criticizing or being critical of your performance in any of your homeworks, okay? So anyway, maybe that's not a problem for anybody, and maybe it's the quizzes that are flustering people and the tests are flustering people, but Yeah, so too many points lost to kind of silly math mistakes. All right, so divide both sides. All right, these cancel out, so n is equal to 11.28 moles of helium. All right, straightforward, right? All right, let's see what the next one is. At an altitude, and we're on 16b now, page 252. At an altitude of 10,000 meters, the temperature now is 221 K. Okay, so now we have a T is equal to 221 K. Pressure, 25 kPa, so 1/4 of an atmosphere about. And now we're looking for the new volume. Okay, so now we know that N is going to be the same because it's a balloon. Okay, and nothing gets in or out of it. All right, so what are we missing? We've got P, V, N, R, T. All right, we're solving for V, so we just need to figure out what R is. Now notice we've switched up units. So no problem for y'all. I know you know what to do. But we'll be back on 235, and which R should we use? All right, we've got kPa. And so that should be, we're going to solve for liters. That's probably the best way to do it. And so we'll use 8.314, and that's liters kPa over mole K. All right, back to PV equals nRT. You guys are already so sick of that, I know. 25, you just got to make sure all your units match all through here. V is equal to 11.28 moles times R, 8.314, 221, and then divide both sides by 25, and we get V is equal to 11.28 times 8.314 times 221 divided by 25, and that is 94. And so we have to look back at our R, and that solves it for liters. Okay, and that is that. Okay, so if the question went further and it said, how does the volume of the balloon change? Okay, you could go to your liters here, and then go to your liters here, and see. All right. So why, if the if the pressure is so much lower, why didn't the balloon expand? Well, because the temperature went down more than the pressure did. Okay, so overall it ended up shrinking. I don't know if that's what actually happens in the real world or not, but that's what our problem says happened there. Okay, and let me pause y'all. I'm going to go check and make sure and I hope you guys were running the numbers and realized I just put it into my calculator wrong, which can happen to anybody. I did really appreciate on you guys' quiz is that some of you showed me some really good work. So this is 829 liters. Sorry about that. I don't know what I did wrong in my calculator. Maybe I don't know. I don't know what I did. Anyway, so some of y'all showed me some really good work, and I was able to just take off 1 point because you made a calculator error. So that's awesome. I love doing that. Okay, so 829 liters. So that's what made me go check it. Is that when balloons go up, even though the temperature does drop, the pressure drops more. In relation to that, and so they do tend to expand and expand and expand until actually they pop, and then the weather balloons come down. So started out at 275 liters, ended up at 829 liters. And so I could ask you, what's the difference in volume between those two things? And you would just work a PV and RT, compare the volumes. Okay? So sometimes you'll be asked something there where you got to do an intermediate step, which is, I know, difficult, because sometimes you're barely kind of hanging on to what you're supposed to be doing, but that's really good critical thinking skills, is to be able to do that intermediate step and then solve for your answer. All right, let's work on another one here. Let's just look at number 24. Okay, this is about partial pressures. Okay, so anytime we're going to see mole percent, that's going to mean we're just doing partial pressures. All right, and remember that partial pressures just mean that they are whatever mole percent they are of the atmosphere, they're just that percent of the total atmosphere pressure. All right. Components of the synthetic atmosphere are 80.5 mole percent. All right. So why is it important that we call this mole percent? Okay, because it doesn't matter about their mass percent. So if we weighed it out, let's say we had 100 grams of air, and we knew that it was 80% by weight or mass, nitrogen, that doesn't do us any good at all. Okay? Because just like when we're doing stoichiometry, it only matters about the moles. All right? So this is unhelpful. So he's doing some of the work for us here. Okay, and it's 80.5 mole percent argon, 18 mole percent oxygen, and 1.5 mole percent CO2. All right. Total pressure, 748 torr. Okay, remember that's also like millimeters Hg, right? And you'll see that in the R values that they're the same when, for the constant, gas constant. Okay. All right. Partial pressure for argon. So we'll call this P argon is equal to the total pressure times, we'll call this the mole decimal of argon. Okay, so P argon, total pressure is 748 times what? 0.805. If you multiply it by 80.5, you're going to get a number that doesn't make sense. Okay, because it'd be way too big. All right, and again, this is kind of like the mass percentages. If I ask you to solve for all of them, so that answer is 602.14 torr. Okay. If I ask you to solve for all of them, you need to check and make sure they all add back up to 100%. Okay, but that's the partial pressure. All right. If this atmosphere is to be contained in a vessel with a volume of 165, temperature is 295 K, how many moles of argon? Okay. All right, and we know the pressure is going to be 602.14 torr. Okay, and I'm going to explain why we use that one in just a second. All right, we're looking for N. What do we mean by PV and RT? All right, so let's go pick our R, and then we'll figure out what exactly we need to do and why we picked that partial pressure instead of the total pressure. All right, so what do we need? We got torr in liters. We're going to use our 62.36 number again. because that's liter per mole K. All right. So what's the deal with this? Okay, why didn't we use 748? Okay, because if we had used 748 for our pressure, we would be solving for the total number of moles in that 165 liter container. Okay, that's not what we want here. We want the number of moles of argon. So what we could have done, we could have used 748 and then known that 80.5% of that was, so we could have solved this whole deal, got the total number of moles, and then multiplied that by 0.805. Okay? When we would just be repeating the math that we did right here. Okay? So if you want to know how many moles of something is in a container, and it's part of a mixture of gases, you can, especially if you've already done it, solve for the partial pressure first, and then use that partial pressure in the PV equals nRT. Okay, and I'll spare you guys from working another direct PV equals nRT, but of course it would look like this. And you guys can pause me and check if you want to. But the solving this, of course, is identical to above. Okay? All right, good deal. Okay, so let's look at something a little more involved. All right, and so we'll skip over to, let's see, 9.3 is partial pressures. We just looked at that. Okay, collecting gas over water. We got to subtract out the partial pressure of water. Let's see, do we have one of those we can work on? All right, let's look at number 27, just so we can remind ourselves that the about the partial pressure of water. All right, let's dive into 27 here. All right, sample of nitrogen is collected over water. Excuse me. There we go. Total pressure. And we'll label this P total. 1 atmosphere. Temperature is 22 degrees C, which is what? 297.15. All right. Nope. 295.15. Excuse me. Okay. And of course, we want to just go ahead and do that so we can just be done with our degrees C, because it's only going to confuse us. Volume is 285 milliliters. Well, we can't do anything with that. And of course, if you need to, you can do your 285 milliliters. So 1,000 milliliters is equal to 1 liter. And that's going to be equal to 285 liters, right? Okay. Do not be too proud to do this, guys. You get some wonky answers if you go the wrong way. All right? All right. Now, want to number the moles. Partial pressure. And the mole fraction. All right, so what are we talking about here? So the deal is, even before you collect anything in that apparatus, okay, and remember, This is the apparatus we're looking at here. This guy on page 246, if you want to look back at it. Before you collect anything in there, or even as you start to push that water down out of there by collecting gas and bubbling up into there, as that gas is going into there, water is vaporizing, turning from liquid to gas, and partially filling that space. So when you think you've collected just pure nitrogen in there, well, you don't have pure nitrogen because you've also got water vapor in there. All right, so let's look at vapor pressure, H2O. Okay, and what does he say? Table A4. So flip back to Appendix A. That's page 390. And you'll notice it's only by temperature. And which one do we want? We want, well, we've got a choice of atmospheres or kPa. I'm sorry, we got a choice of torr or kPa. Let's just do kPa. All right, so we'll just go ahead and get rid of the atmospheres and just go ahead and do 101.325 kPa, and then we'll get our partial pressure in that as well. We're at 22 degrees, and so that puts us at 2.6453 kPa at 22 degrees. Okay. All right. So now what do we do with that? Let's see. We need to do PV nRT. Or do we? All right, yes, we do need to do PV equals nRT after we got the pressure of the nitrogen is equal to the pressure atmosphere minus pressure of the H2O. Okay? And then we'll take this pressure and put it right there. So what do we have? 101.325 minus 2.6. We'll just do 2.65. Okay? And why do we do that? Okay, because we've got a total amount of pressure, and that water vapor is eating up some of that pressure inside that vessel. And we know for that, for that gas to bubble up into there, because that is going to be full of water, and we got the tube bubbling into there, and it's slowly going to look like that. Okay, and eventually it's going to fill, right? And for there to be, this pressure has got to be equal to this pressure. This is a terrible drawing. I'm doing an awful job here, but basically these have got to be equal, and so we know that the total kPa has got to be doing that. So and this is vaporizing in here to fill that space as well. So we'll do that math, and we'll get 101.325 minus 2.65, and that's 98.675. Okay, and we'll plug that in here. Sorry, times 0.285. and we're looking for the number of moles. All right, and R we need to get. We're going to do kPa and liters. So once again, we flip back to 235, and that's 8.314. And sorry about that. 295.15. So N there is equal to 0.0. Okay. Of nitrogen. All right, so that's our first answer there, and then our partial pressure is just the partial over whole. And so what's that going to be? What's our partial pressure? 98.675 over 101.325. So that is 0.97, which goes to 97%. So we should see that it's most of it, because the total amount of pressure is 101.325. Water only makes up 2.65 of it, and so 98.675 is what is left over, which is obviously most of that pressure. Okay, so we should expect something in the upper 90s, and we do get that. It's 97% there. All right, and then what's the final one? Mole fraction. Okay. Wait a minute. This is actually the partial pressure. Sorry. This is the mole fraction, or mole percentage. Okay. Again, let me make sure I'm not going off the rails there. 7. Yeah, I'll check me on some of this stuff when I'm just going through and working these problems here. 0.011 moles, 0.97 atmospheres. Yep. Okay. Good deal. All right, and I'm not going to go through and work B because it's exactly the same. Okay. So that's how we work a partial pressure one, and you guys, kind of note where these are in the videos if you need to rework some of these to get prepared for the test. Okay. All right, and finally, let's work one of the stoichiometry ones, which is basically what we've been doing all along. Now that we know stoichiometry, and now that we know the ideal gas law, we can combine them to do things like number 30. Okay? All right, so carbon monoxide reacts with O2 to produce carbon dioxide. All right. We want to know liters of oxygen. And that is reacting 5 liters of carbon monoxide. And how many liters CO2 are produced. All right, so we're going to assume standard temperature pressure. All right, so what's that? Pressure is equal to 1 atmosphere. Temperature is equal to 21 degrees or 296.15 Kelvin. No, it's at 0 C. Oh, sorry. 273.15 K. All right, and let's see what we need to do. All right, what's the first thing we need to do? We need to balance. Okay, can't do anything until we balance. All right. So y'all need to be writing these steps down here so that when it comes time to solve these problems for yourselves, you can just say, all right, what's the first thing I need to do? Balance. Okay. And then you don't worry about any of the other steps until you've got that one handled. And then you move on to the next one. Okay? All right. You should have a general roadmap in your mind, which I'm sort of trying to give you here. But other than that, you just go one step after the other, okay? And you work them until you're pretty confident you can work any kind. Okay, so what do we got? We got 1C, 1C, that's good, that's balanced. But we got 3 O's and only 2 O's. All right, so what can we do? Well, we got this odd guy right here, which is going to make it hard to balance because I can only multiply. I can do 1, 2, 3. That's going to give me 2 oxygens, 4 oxygens, or 6 oxygens, which doesn't help us over here. Okay, so let's get rid of that being an odd and put a 2 right there. And we'll also put a 2 right here to balance out the carbons. Okay, so we got 2 oxygens, 4 oxygens, 4 oxygens, 2 carbons, 2 carbons. Now we're balanced. Good deal. Okay. All right, so now we have a balanced equation. Secondly, we need to solve using stoichiometry. And then we worry about the liters once we're in moles, okay? So that, remember, means get to moles and end in moles. Well, and get to moles and work in moles, and sometimes you got to get back out into grams, but here we're going to be in liters, okay? So we're going to get to moles, and let's say we're going to work in moles. All right, so what do we have? Well, since we're at standard temperature and pressure, we know that 1 mole of any gas equals 22.4 liters. Okay, so this is a value you need to memorize. Okay, and really that is not that big of a deal because anytime you get stuck, you can plug this P, this T, the R you need, and a volume you have, and solve for the number of moles, or plug in 1 mole and then solve for the volume, and you're going to get 22.4. Okay, so let's know that this is reaction. We got 5 liters of CO, so we're going to say 5 liters of carbon monoxide and 1 mole of carbon monoxide is 22.4 liters. And what's that going to get us? Five divided by 22.4, it gives us 0.22 moles CO. Okay, so I'm going to put 0.22 moles up there. And what do we want? We want to know the liters of O2. Okay, so now we just take 0.22 moles of CO, and it's as if I had asked you, how many moles of O2 does it take to react with 0.22 moles of CO? Okay, so 1 mole of CO, carbon monoxide, needs, 2 moles of carbon monoxide is reacting with 1 mole of O2. And so we see that that's going to be what? 0.11 mole of O2. And then we just take that, 0.11 mole of O2. And you could do all this in one step if you wanted to. You know, just rack them up like that. All right, what's it? That. And then we know that 1 mole of O2 is 22.4 liters. Okay. And that ends up being 2.5 liters O2. Okay. Now this happens to be a nice even ratio there. All right. We probably could have done a little shortcutting if we'd have realized that a 2-to-1 ratio in stoichiometry equals a 2-to-1 ratio in liters. But we needed to work through this to be able to talk about it pretty coherently. Okay. But now that we know that relationship, how many liters of CO2 do you think are produced? We got a 1-to-1 ratio or a 2-to-2 ratio. Darn it, sorry. 2-to-2 ratio right here. Okay, if we go in with 2.5 liters here, 2.5 liters there, well, we're back to 5 liters on this side because it's a 2-to-2 ratio, so the number of liters should be the same on both sides. And so our answer should be for this one also 5 liters. Okay. All right, so pretty straightforward there again, even though it's built on stoichiometry, which is really not super straightforward, and it's been a while since we've done it. Okay, so we'll need to be very careful as we work through those to make sure that we're hitting all of the steps very carefully. Okay, if you don't remember to balance, your whole thing is going to be off. Okay. And then you can get to moles and work that. And then you can get it into whatever you want. If they want a volume of it, that's fine. Or if they want the number of moles produced, also fine. If you want grams of it that's produced, no problem. Because once you get to moles, the moles to grams work just like anything else. Just like any other stoichiometry, just because it's a gas doesn't change that deal. Okay? Okay. Well, I am gonna call that a day for this lecture, and I'm gonna either let you guys work some more problems from the book, or I'm gonna get some sent in for you guys to work. But that's really just kind of where we're going to focus. And then on, what's today? Tuesday. On Thursday, you will see that we have, let's see. All right, we're going to lecture 10.1. So you'll need to do whatever 9 homework gets assigned. I haven't formulated that yet. And you'll need to read chapter 10 and start 10.1. Why do you ask? Are we going on to 10 when we haven't finished 9? Well, because we're about to be out of time for the year. And so we've got to push through a lot of this stuff. And I wanted to give you guys time to finish chapter 9 homework. Ask me any questions that you had. Me be able to answer those in time for you guys to be ready for the test on Tuesday for chapter 9. So I hope everybody's got their lab report in by now. And I look forward to reading those and working through those. And then we will push on to the chapter 9 test and get started on chapter 10 on Thursday. Okay? I appreciate y'all.